Take a look at pre-lab exercise 2. There are some definite differences between pre-lab exercise 2 and pre-lab exercise 1. One is that we are now going to be discussing a proportion test instead of numeric mean test. And two is that they're not going to give us alpha, they're going to give us a decision rule, and then we're going to find alpha back. So they've started by saying there's some context to the situation, but basically if less than 20% of households say that they're going to buy a certain product, then perhaps they're either not going to produce it or they're going to sell it at a whatever price. Okay, so they're going to ask 300 people, and they're really wondering if the proportion of people that will buy this is either at least 20% or equal to 20%, or if it's significantly less than 20%, because they really want an idea of how to market this product. Okay, so they gave us the null hypothesis and the alternative hypothesis. I've written it here. And then they've asked just for us to describe a type 1 error in context here. So type 1 is reject the null hypothesis given it's true. Type 2 is fail to reject the null hypothesis given it's false. What does rejecting the null hypothesis mean? Here, if you rejected this idea of p being equal to zero point 0.2, then you would be here in turn forced into this idea. So if you rejected the null hypothesis, uh, sorry, these are actually mixed up as I look at this. I'm really sorry about that. So if you rejected the null hypothesis, then what you'd be saying is you believe the proportion of people is actually less than 20%. When it's actually at least 20%, when the null hypothesis is true. So here, this explanation should be actually the explanation for type 1, and this explanation should be the explanation for type 2. Sorry, I really apologize about that. So here, the probability of making a type 2 error would be failing to reject the null hypothesis, or in other words, believing that the proportion really is greater than or equal to 20%, but it's actually less than 20%. So here there is a bit of a typo. This is not the typo. Type 1 is rejecting the null hypothesis given it's true. However, the explanation for rejecting the null hypothesis given it's true is actually found here. And type 2 is correctly failing to reject the null hypothesis given it's false, but the description of that is actually up here. So really apologize for that. Sorry. Let's just scroll so we can't see that anymore. Okay, so is this a left-tailed test, yes or no? And why isn't it a two-tailed test? Again, here, really what we're trying to indicate is a number such that it would suggest that the proportion of people really is less than 20%. Okay, so they were particularly interested in if the proportion was less than 20%. So as I read this, and I'm kind of scanning along. Um, you really need a 20% and not less. However, like if you had more than 20% in this context of trying to have a marketable thing, of course you would love it if the population, if more than 20% wanted to buy your product. Really what you're scared of here is the other end where less than 20%. So that's why you don't really care if more than 20% are interested in buying your project. In fact, you would love that, but that right there, what we're really worried about is if it's less than 20%, we won't be able to make our company float, or we're going to have to make some significant changes to products or whatever. However, however, if the proportion of people who want to buy the product is more than 20%, that's obviously good news for us. We're not concerned about that, which is why we're really only worried about the lower cutoff and not the upper cutoff here, making this a left tail test and not a two tail test. So here we're not worried if it's greater than 20%. In fact, that would be very, very beneficial. Okay, so then it goes on and says, okay, the sample size is going to be 300. And they are going to say, if you find, really, we are hoping that the proportion of people who want to buy this is not less than 20%. However, we realize that when you take a sample, not every sample is going to be perfectly accurate when compared to the whole population. So if you took a sample and during that sample you saw that the proportion of people that were interested in buying was less than or equal to 15.66, and I know that's not 20, but here you're saying I'm going to give myself a little bit of breathing room. If my sample was exactly 20% or a little bit less than 20%, perhaps the actual proportion could still be 20 or more than 20%. So I'm going to give myself a little bit of tolerance and say, I'm only going to draw the line in the sand and say that the value uh, of 15.66 is significantly less than 20%. So once it's this low or lower, I'm going to say that's low enough to feel like that's not even in the same ballpark anymore. So what they've given us here is they've actually given us the critical value. We're actually used to being given alpha and then finding the critical value. But in this case, they've given us the critical value and then they're asking for us to calculate alpha based off of that. So they've actually given us when we would reject the null hypothesis and when we wouldn't in terms of sample proportions. Now, there are a few different scales that you can think of this same sort of critical value. One is here in proportions, this is 15.66%. In terms of number of successes out of 300, if I just take 300 times by zero point 0.2, I get 60. And if I take 0.1566 times by 300, I get 46.98. So here we are talking in X scale, we're talking about the number of successes out of 300 to make this go well. What we're expecting is out of 300 people, 60 of them will say they want to buy our product. However, and you can see that this is this is not a whole number. So here, if we have 46 or fewer out of 300 who say that they would buy our product, then we know that we're going to decide to say that the proportion of people who want to buy our product really is significantly lower than 20%. And if we have 47 or higher out of 300, we would fail to reject. We'd say, yeah, the proportion is at least 20% that appear to want to buy our product. So here, it's true that the critical value in terms of number of successes was actually not a whole number. But when you're talking about the number of successes that could happen out of 300, we know that this number is not possible. So you're either talking about a whole number 46 or a whole number 47. If it's 47, you're in the fail to reject region. And if it's 46, you're in the reject region because this number, if it's not a whole number, is not actually possible. And then also we could use the formula here. This is p hat minus p over square root of p times 1 minus p all over n to find what this proportion is in terms of standard deviations or z-scores. So here you can either talk about the critical value in proportions, in number of successes out of 300, or in standardized deviations. We can, from any of these values, I guess, go from these values to find what this area is, which is the probability of making a type 1 error. Okay, so here, what's the probability of making a type 1 error? What I need to do is find out how much area is on the left, because it's a lower tail test, of this critical value. So I can do that by using the command pnorm of here, this is the critical value in terms of p hat. If you're using a critical value in terms of p hat, then the center is actually 0.2, and the spread is actually the square root of p, which is 0.2, times 1 minus p, which is 0.8, divided by n, which is 300, and then take the square root of that. Alternatively, if you want to find the area that's on the left side of the standard deviation or z-score, critical value, then once it's a z-score, you could just use p norm of the z-score because the middle is 0 and the spread is 1. Either way, if you use this command or you use this command, you should find pretty much the exact same answer. Maybe some rounding might change it. But what we've seen then is the area on the left side of the critical value is about 3%, which means here alpha is not always at 5%. I mean, usually there's a good default chance that it could be 5%. But when we had a critical value specified for us, the corresponding alpha actually was about 3%, not 5% here. So here, that is the level of alpha that they used if they are going to have a critical value of 15.66%. Okay, so then they're saying they actually took a sample. Pretend you actually took a sample, and the sample turned out that out of the 342 said that they would actually purchase the product. So we can use this in any number of ways. We could find the sample proportion by saying 42 out of 300 is 0.14 as a proportion. We could use it just as the number of successes, which happened to be 42, or we could actually calculate this into a z-score. So here, these are the critical values in terms of proportion, successes, or z-scores. Here, the sample proportion is 42 out of 300, which is 0.14, which unfortunately is on the left side of the critical value, which means we would reject. We're in the rejection region. If you were looking at just strictly successes, instead of saying 42 out of 300, just 42 is again on the left side of the critical value in terms of number of successes, which is 46.98. So here we're also in the rejection region. And finally, if you wanted to calculate the test statistic in terms of a z-score, this would be p hat minus p over p times 1 minus p over n square root, which you would find a test statistic in terms of z-scores of negative 2.6, which again, if comparing to the z-score critical value, is of course all on the left side of all of these critical values, which means that you would reject the null hypothesis. The other way of doing this is to find the test statistic in terms of z-scores and then find its p-value. So we are using the distribution of the normal distribution here because we're talking about proportions for categoric data. And here, this is the test statistic in terms of z-scores, so I've calculated it there. In this case, the p-value is going to be the area in the tail. Which tail? Whatever tail the alternative hypothesis is talking about. So in this case, it's a lower tail test, so the p-value must be in the lower tail, which means that the probability of here the z distribution being less than the test statistic, or in other words, the left tail of the test statistic, will be the p-value. Okay, so I did find the p-value here, and now one thing you do have to be very careful of, you're so used to always alpha being 5% that you might be thinking that you should compare this to 5%. But remember, earlier in this question, we found that alpha was not 5% here, but actually about 3%. In any case, our p-value is quite small, so what I mean by quite small is smaller than alpha. So here, this number, 0.004687, is smaller than the number 0.03, which was alpha. Okay, so that's one way of finding the p-value. There are additional ways of finding p-value. So here I sort of calculated the test statistic by hand and then just found the tail area using R. Of course, you could use here the BSDA package if you like. So here, the BSDA package, the only thing you have to be careful of is instead of using t-sum, if you didn't know the population standard deviation, here we're going to use z or z-sum because this is a test on proportion. So if it's a test of proportions, then here the first thing that you need to give it, the function, is the sample proportion, which was 42 out of 300. Then you need to give it sigma. So what is sigma going to be here? Sigma is going to be p times 1 minus p, and then the square root of that. So here, the standard deviation, the population standard deviation of a proportion is p times 1 minus p, all under the square root. Okay, and then the sample size, of course, is 300. The alternative sign was the lower tail, or the less than sign, and the hypothesized proportion was zero point 0.2. And you could put in here the confidence level, which is 1 minus alpha. So here we found that alpha was actually 0.03010, not quite sure, but here we found alpha to not be 5%. We found it to be around 3%. So I'm just going to put in that many digits. And you can see it's going to find you the test statistic in terms of Z. It's going to find you the p-value, which we've also already done. But it's just another way of calculating it, if you like. Okay, so we've confirmed that the p-value really is somewhere around 0.5%, so 0.0047. I guess it would round to that. So yes, we've confirmed that that is in fact true. And now they're saying perhaps our hypothesis was, let me just see if I've redrawn this. Oh, no, I haven't. So we believed that the proportion was 0.2, but perhaps it's actually, the true proportion is actually 0.17. Okay, so here we've developed our rejection plan based off of the proportion being 0.2. But what happens, and then we found critical values. But what happens if the center of the curve really isn't 0.2? What happens if the center of the curve is actually 0.17, if that's really the real truth? So here, off of the curve that was based off your null hypothesis, this will develop the critical value as well as what alpha is. And now that the critical value has been established as here 0.1566, then what if the center of the curve really isn't at the null hypothesis? What if it's at something else? Then you are talking about curves that don't tell you about alpha and 1 minus alpha. You're talking about curves that tell you about power and the probability of making a type 2 error. So here, one thing to remember is on a lower tailed test, alpha is always on the left tail, and so is power. On an upper tailed test, then alpha will always be on the right test, and so will power. So in this case, when we are trying to now find the probability that you will conclude that 20% of households will purchase this product, what you are trying to find is here, what's the probability that we will believe or conclude that the proportion really is 0.2, which means, in terms of the null hypothesis, that we would fail to reject the null hypothesis. So what's the probability that you believe this idea, okay, but the null hypothesis is actually false? Okay, so we would believe that the proportion is actually 0.2, but the curve isn't actually centered at 0.2, it's actually centered at 0.17. So in other words, I would be saying, what's the proportion of failing to reject the null hypothesis given the null hypothesis is actually false, which is actually an error, right? So if you are believing something but it's false, that's an error. And in this case, that type of error would be a type 2 error, which is given the symbol of beta. So really what this question is saying is, what we're looking for is, what is the probability of beta, or what is the area here on the left side in this lower tail test? Sorry, I said left. What is the area on the right side of this lower tail test, or what is the probability of beta? So what I'm trying to find out now is, I can continue to use the same critical value, which is 0.1566, here to be where I'm rejecting and where I'm failing to reject. However, this curve is not based on the center being 0.2, which is the null hypothesis. This curve is actually being based on the actual truth, which is 0.17. Okay, so that's why this area is not 1 minus alpha, because it's not based on the null hypothesis. Okay, whereas here, this area is 1 minus alpha, and this area is alpha. On this curve, because it's not centered at the null hypothesis, this area is actually beta, and this area is power. So how do I find this area out? Well, I can find here the right tail by finding the area of the left tail and then doing 1 subtracted. So if I do 1 minus p norm, so p norm gives me the left tail, but 1 minus p norm gives me the right tail. So if I do 1 minus p norm of this value, that is the critical value, however, the center is no longer 0.2, it's now 0.7. And here's where you want to be a little bit careful. The standard deviation of the hypothesized curve was p times 1 minus p, all under the square root, right? And in this case, p was 0.2. But now the standard deviation has changed because now the center is not zero point 0.2 anymore. So the center we do change, right? So instead of the center being zero point 0.2, it's now 0.17. But the standard deviation has also changed. Instead of the standard deviation being zero point 0.2 times zero point 0.8 divided by 300 all in the square root, it is now 0.17 times 1 minus zero point 0.7 divided by 300 all under the square root. And then you can find here now the area that is on the right side of the critical value, which would in this case be the probability of making a type 2 error, or beta. Okay, so here we found the probability of making a type 2 error, which is that we would believe that the null hypothesis is actually zero point 0.2 when it's actually 0.17. It's just about 73%. And finally, then the last question says, well, what would happen if instead of only asking 300 people, you asked more than 300 people? Okay, so you could look at the formulas and see where n resides in the formula. And because it's in the denominator of a denominator, it might go up or down. It might be a little bit confusing, whatever. Here, this is the way that I think about it. When the sample size goes up, what does that mean generally? When you're getting more information, then that should mean that your estimates are better. You've got, like, the more information you have, the better guesses you should be able to make. And if you are making better guesses, then the probability of error will go down. So if sample size goes up, then the probability of error will go down. And what are your errors? Beta is an error, it's the probability of type 2 error, and alpha is also an error, it's the probability of type 1 error. So if sample size goes up, then the probability of making an error goes down, in this case, in both situations. This is sort of unique because typically the probability of making a type 1 error is inversely related with the probability of making a type 2 error. So generally speaking, when probability of alpha goes up, usually the probability of beta goes down. But the only way to make them go in the same direction as they are here is when you manipulate the sample size. So the only way to make both errors go down is by getting better estimates, and better guesses only come from having more information. So this is a bit unique that you can get both alpha and beta to both go down. It only happens when you have the sample size going up.